Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, in the last session we explained what is interplanetary magnetic field, and we have seen how the interplanetary the magnetic field is it behaves in the sun's outer atmosphere, that is the corona, and how then it is transported or driven by the solar wind to the interplanetary space. Then we described how this magnetic field and the solar wind it co-rotates with the rotation of the sun, and there is the interaction of slow solar wind as well as the fast solar wind, and that gives rise to co-rotating interaction regions. So, co-rotating interaction regions means, as we explained, that it generates the shock waves of it is a forward shock waves as well as the reverse shock waves. So, in order to explain this two phenomena, that is the interplanetary magnetic field IMF as well as the co-rotating magnetic regions, we explained what is the coronal structure, what is coronal lobes, then what are the open streamers, then pseudo streamers, and the helmet streamers as well as the coronal holes. So, today in this session I will explain how this magnetic field reaches to the our Earth's magnetosphere and how it interacts, that is the solar wind interacts with our Earth's magnetic field, that is called the magnetosphere. So, our today's the topic is coupling of solar wind to the Earth's magnetosphere and the ionosphere. So, here we will see the phenomena, this is called the geomagnetic storm and geomagnetic substorm and the geomagnetic indices. So, geomagnetic indices basically this is the matrices by which we know what is the magnitude of the geomagnetic storm, how severe is this storm. So, let us now see how the solar wind and the magnetosphere interaction happens. So, in this illustration you can see the solar winds. So, this is the corona, the solar winds guided by the that is or along with the magnetic field, it reaches to the our sun's magnet, that is our Earth's magnetic field, the magnetosphere. And you see this our magnetic field is here is not symmetrical. I will show you in the next figures. In fact, when I do not consider the interaction of the solar interaction, the magnetic field, the Earth's magnetic field is a dipolar, it is symmetrical. But you see in this case where the day side, where it is looking to the sun side, it is compressed and it is elongated in the on the other side. So, what happens whenever the solar wind reaches the earth, it sends a flurry of the charged particles into the magnetosphere along the earth's magnetic lines towards the poles. Now, the charge it gets trapped by the magnetic field, it cannot cross the magnetic field. So, this is the properties of the charge, a moving charge. When a moving charge, a charge moves in the magnetic field. So, the charge gets trapped or it gets gyrated by the magnetic field. So, as a result of this thing, those charged particles it cannot enter directly to our that is the magnetosphere. And we will see that the interaction of these particles with the Earth's atmosphere, it produces the glowing aurora displays above the polar regions. When the solar wind encounters the earth, it deflects by our planet's magnetic field, causing most of the solar winds energetic particles to flow around and beyond. So, the region that meets and blocks the solar wind, it is called the magnetosphere. So, this part we will call it the magnetosphere, this part is called the magnetosphere. So, the solar wind flows continuously and that the outward flow carries along the solar magnetic field, and the rotation of the sun results in the fields being drawn out in a spiral pattern, that already we have seen, and whose angle that depends on the velocity of the wind. So, here we can see that is this is the IMF, that is the magnetic. So, these lines, if I consider these lines are the interplanetary magnetic field, and if you see this is the direction is the southward direction. Okay. So, in this region, so there is a magnetic reconnection happens and the magnetic field breaks down. Okay. So this region where this happens, so you can see this whenever the magnetic field is this is the IMF, it is interacting with the Earth's magnetic field, something like a bow shock is formed. So, in the next slide I will try to explain what is the bow shock, and then there is there is a boundary that is called the magnetopause. So, in the magnetopause what is happening, that is the magnetic pressure of the IMF and the Earth's magnetic, that is geomagnetic field, they cancel each other, their intensity is the same. So, this is called the magnetopause. So, inside the magnetopause will not find this the IMF. So, as if it is shielding it. So, the simplest view of the total phenomena is that the magnetosphere presents an obstacle. So, it just presents obstacle to the passage of the solar wind in a manner something like a blunt body in aerodynamic flow. The interaction of the flow that results in a shock wave followed by a shocked gas region and the boundary layer of the subsonic flow around the magnetosphere, with the free surface of the magnetosphere itself determining the detailed flow properties near the boundary. So, what is a shock wave? So, basically a shock wave is a type of the propagating disturbances that moves faster than the local speed of the sound in the medium. So, this in the physics this term is used. So, like an ordinary wave, the shock wave carries energy and can propagate through a medium, but is characterized by an abrupt nearly discontinuous change in pressure, temperature and the density of the medium. So, already we have seen that is the co-rotating interaction region, there is a reverse forward shock and there is the reverse shock, because of the discontinuity of the velocity of the first solar wind as well as the slow solar wind. And here it shows that is how this magnetic, that is co-rotating magnetic field when it is spreading in the interplanetary space, if you consider the earth in between. So, it forms a sheath and you are having a forward shock as well as a reverse shock. So, the reverse shock, whatever we have seen in the earlier picture, that reverse shock, it interacts with the Earth's magnetic field, and as a result of that we get a something like the bow shock or the magnetopause. All these things, the results of this when this the shock wave, it interacts with the our sun's our Earth's magnetic field. So, now let us see what is the how the Earth's magnetosphere looks like. The magnetosphere is the region around the planet dominated by the planet's magnetic field, and other planets in our solar system is they have also magnetosphere, but Earth has the strongest one of all the rocky planets. It is basically this magnet. The Earth's magnetism is formed because of a phenomena called the dynamo mechanism, and the similar thing happens in the sun also. This is for the all planet stars, the reason that it is having a magnetic field is because of the dynamo effect. So, as you see, when we do not consider that is the interplanetary magnetic field as well as the solar wind, the magnetic field lines are very much symmetrical. It is very much symmetrical. This is the lower one shows a the 3D illustrations of the magnetic field lines, and so this is in the absence of the any disturbing field like the interplanetary magnetic field, and it is so this the life on the earth, it is been saved by this the magnetic field. So, whatever the charged particles, they cannot directly enter to the our Earth's atmosphere. Of course, Earth's atmosphere also saves us from the harmful radiation of this. So, the magnetosphere, it as I said, it shields our home planet from the solar and the cosmic particle radiation, as well as the erosion of the atmosphere by the solar wind, the constant flow of the charged particles steaming off the sun. So, when the solar wind encounters the earth, it is deflected by our planet's magnetic field. So, as we have already seen in the earlier illustrations, it is deflected, it cannot directly enter to the Earth's space. So, as if the magnetic field, it deflects it. So, So, because of this Earth's magnetic field, this causes most of the solar wind's energetic particles to flow around and beyond us. So, the region that meets and blocks the solar wind is called the magnetosphere. Now, what is bow shock? So, we can understand the bow shock by illustration. So, it owes its name to the analogy of the bow wave that. So, the bow shock owes its name to the analogy with the bow wave that appears on the surface of the sea when a ship is moving through the water. So, when a ship is something like the obstacle towards the against the current, and so what happens, whatever just the nearby that the boat, the particles or this current, the water particles, they got deflected. In fact, that speed is reduced there. So, similar thing happens whenever the Earth's the solar wind guided by the interplanetary magnetic field, it interacts with the sun's magnetic Earth's magnetic field. So, in the bow shock, if I want to define it, it is the boundary at which the speed of the stellar wind abruptly drops as a result of its approach towards the magnetopause. So, this illustration shows how the solar wind when it is moving. So, this a bow shock is formed like that thing, and all this the solar wind, they are deflected, they cannot enter to the magnetosphere. So, they are shielded by the magnetopause or magnetosheath. So, the bow shock is the shock surface where the solar wind is suddenly slowed down from the supersonic to sonic velocities. This already I said what is a magnetopause. So, this is clearer when I consider these illustrations. So, again you see this is the interplanetary magnetic field and this along with the thing solar wind, and then it is interacting with the Earth's magnetosphere. So, there is a magnetosheath. So, this boundary is called the magnetopause. So, this is the boundary over which. So, inside this you are having the magnetosphere, and this boundary where this speed reduces, this is that interacts with the magnetic field, this we are calling the bow shock, that already we explained. So, the magnetopause is the abrupt boundary between the magnetosphere and the surrounding plasma. So, the magnetopause is where the pressure of the interplanetary magnetic field, it balances that of the geomagnetic field. And in planetary science, the magnetopause is the boundary between the planet's magnetic field and the solar wind. Now, the location of the magnetopause, it is determined by the balance between the pressure of the dynamic planetary magnetic field and the dynamic pressure of the solar wind. As the solar wind pressure increases and decreases, the magnetopause moves inward and outward in response. So, this magnetopause is not fixed, again it depends on what is the dynamics of the solar wind. So, during the solar activity or the solar maximum or solar minimum, this magnetopause, that is the location of the magnetopause, will vary. So, the next is the magnetotail. So, what is the magnetotail? As we understand by the name magnetotail. So, some form of a tail is formed by the night side of the. So, one is the sun side, and we have seen this interplanetary magnetic field. It is swept away in the towards the back side of the day side. So, that is called the magnetotail. So, the magnetotail is the region of the magnetosphere of a celestial body like our Earth that is swept back by the solar wind in the direction away from the sun. So, you can see this one. So, this portion, it is called the magnetotail. So, this portion, and here this is called the tail lobe, and so this part already we explained what is the bow shock and the magnetopause, magnetosheath. So, in contrast to the day side of the magnetosphere, so day side is compressed and confined by the solar wind, the night side is stretched out. So, this is just opposite. Wherever in the day side, the magnetic field lines of the geomagnetic field lines are stretched towards the center of the earth, whereas during the night time it is getting elongated and it is getting stays out. This part of the magnetosphere is quite dynamic, and large changes take place there, and ions and electrons are often energized. This we will see when we explain the geomagnetic storm and geomagnetic substorm. How the in the magnetotail, because of the magnetic reconnection, these plasma particles, that is the solar wind, the particles, how they get become more energetic, and then it moves towards the earth, and it gives rise to various phenomena like geomagnetic storm and geomagnetic substorm. So, already I said the reconnection between the magnetic field lines in the earth's magnetotail under disturbed geomagnetic conditions. So, this results in the acceleration of the electrons into the high atmosphere, producing active and sometimes extensive displays of the aurora, and this also interacts with the spacecrafts, and it can will see how this type of energetic charged particles, they are very harmful to our spacecrafts. So, this magnetic reconnection, what I said, this is happens whenever this magnetic field lines, that is two opposite directed magnetic field lines, they get. So, magnetic reconnection means there is two opposite directed magnetic field lines, they touch each other, and then the magnetic energy, whatever the stored magnetic energy, that is transferred to the particles and as a kinetic energy. So, the temperature of those particles, they are enhanced, and this gives rise to the phenomena like geomagnetic storm as well as geomagnetic substorm. So, now let us try to explain what is geomagnetic storm. So, we will take the case of the southward IMF, and as you have seen, there are two locations where there is the phenomena of the magnetic reconnection is happening. One place where there is the day side, and the other is during the tail side or the night side is happening because of this interaction of this IMF. So, here we are considering a southward IMF. So, and this gives me another view in to understand that how solar wind is getting coupled to our Earth's magnetosphere. So, this geomagnetic storm, these are triggered by the Earth's when the Earth's encounter with the southward IMF. So, this is Earth's magnetic field encounters with the southward IMF. When the high pressure regions are formed and the interaction of low and high speed solar wind streams that co-rotate with the sun. So, geomagnetic storms are classified either as recurrent or non-recurrent. Recurrent storms, this corresponding with the sun's rotation over the 27 days, and as I said, this is 27 days at the polar region and 25 days at the equatorial region. So, this recurring storms most frequently occur during the solar minimum and the declining phase of the solar cycle. Non-recurring storms frequently occur during the solar maximum when the solar cycle is at its high peak, and these storms are caused by coronal mass ejections CMAs, and already you know that CMAs is a collection of the charged particles, and typically the CMAs encounter with the interplanetary shock waves. Now, in order to understand how the geomagnetic storm and substorm happens, just let us consider this illustration. So, as you have seen, so here there is a magnetic reconnection, and then there is the re-looping of the magnetic field. So, exactly how it happens, just it can be explained by this illustration. So, this is a southward IMF which is interacting with the that is the northward geomagnetic field, and this is the reconnection point. So, then it settled down like this, and formally, and then based on the what is the pressure, what is the intensity of this solar wind, or that is it can in the event of coronal mass ejections or the solar flare. So, this things happens, and then there can be this is the reconnection happens, and when the reconnection happens that it snaps back. So, here it is this the particles energy becomes particles energy gets enhanced. Okay. So, this already I said, that is a geomagnetic storm occurs when there is a very efficient exchange of energy from the solar wind into the space and surrounding the earth. So, this happens this energy exchange, it happens by the magnetic reconnection, and these terms results from the variations in the solar wind that produces major changes in the current plasma and the fields in the earth's magnetosphere. Solar wind conditions that are effective for creating geomagnetic storms are sustained. It can be from several to many hours, periods of high speed solar wind, most importantly southward directed solar wind magnetic field. So, this all southward of the magnetic field opposite to the direction of the earth's magnetic field at the day side of the magnetosphere. The condition is effective for transferring energy from the solar wind into earth's magnetosphere. So, this is the way, that is the energy of the or the interaction of the solar wind with our geomagnetic field it happens, and this gives this type of phenomena like the geomagnetic storm. Now, geomagnetic substorm. So, a substorm sometimes referred to as a magnetospheric substorms or an auroral substorm is a brief disturbance in the earth's magnetosphere that causes energy to be released from the tail of the magnetosphere and injected into the high latitude ionosphere. That whatever we explained in the previous slides, how that is the energy can be released from the tail of the magnetosphere, and the particles goes back and can be coupled to the auroral regions. Virtually, a substorm is seen as a sudden brightening and increased movements as the auroral arcs. Substorms are first described qualitatively in terms of Christian Berkelenge, which he called the polar elementary storms, and Sidney Chapman used the term substorm about 1960, which is now this standard term. Now, what is the difference between the geomagnetic storm and geomagnetic substorm? Basically, the substorms are distinct from the geomagnetic storms. The latter takes place over the period of several days and are observed from anywhere on the earth, and it inject a large number of ions into the outer radiation belt and occurs once or twice a month during the maximum of the solar cycle and a few times of year during the solar minimum. Substorms, on the other hand, it takes place over a period of a few hours and are observed primarily at the polar regions, do not inject many particles into the radiation belt, and are relatively frequent, often occurring only a few hours apart from each other. Substorms can be more intense and occur more frequently during a geomagnetic storm, when one substorm may start before the previous one has completed. The source of the magnetic disturbances observed in the earth's surface during a geomagnetic storms is the ring current that will. So, basically because of the ring current, it opposes the earth's magnetic field. So, during a geomagnetic storm, what we find, there is a decrease in the earth's the horizontal component of the earth's magnetic field. So, we will come to that. This is called the indices, and that will be explained in the next slide. So, as I said, I mentioned ring current. A ring current is an electric current carried by charged particles trapped in the planet's magnetosphere. It is caused by the longitudinal drift of the energetic particles at the range of 10 to 200 kilo electron volts. There are some matrices, or there are some terms by using which we can understand what is the magnitude of the geomagnetic storm. So, these are called the geomagnetic indices. There are various indices like KP index, AP index, then DST, then symmetrical age, sim age. So, I will try to explain a few of them. What is K index? So, K index is basically a quasi logarithmic local index of the 3-hourly range in the magnetic activity relative to an assumed quiet day curve for a single geomagnetic observatory site. It was first introduced by J. Battles in 1938, and it consists of a single digit from 0 through 9 for each 3-hourly interval. and it is derived from the maximum fluctuations of the horizontal components observed on a magnetometer during a 3-hour interval. The level k comes from the German word, that is Kanziffer, meaning characteristic digit. Planetary k index or Kp index, the planetary 3-hour range index Kp is the mean standard of the k index from 13 geomagnetic observations between 45 degrees to 60 degrees northern or southern geomagnetic latitude. Kp is an indicator of the disturbances of the Earth's magnetic field and is used by the space weather prediction centers to decide whether a geomagnetic alerts and warnings need to be issued for the users who are affected by these disturbances. Now, the scale 0 to 9 is expressed in thirds of a unit, means 5, it can be like 5 minus, it can be 5 is 5 minus is 4, 2 by 3, 5 is 5 and then 5 plus is 5 1/3. So, this way from 0 to 9 again there are 3 more indices are put in between. So, this planetary index is designed to measure the solar particle radiation by its magnetic effects. The 3-hourly AP index is derived from the Kp index as follows. So, this shows that is how the Kp index is AP index is derived from the Kp index. And another index is called the GST index. This is the disturbance of the storm time. As I said, because of the when there is a geomagnetic storm, there is a decrease in the Earth's magnetic field because of the ring current, and this gives disturbance in the. So, this is called the disturbance storm times or DST index. So, a negative DST value means the Earth's magnetic field is weakened. This is an hourly index. Then another is the CMH is essentially the same as the DST index, but having a different time resolution only, and it is having a 1 minute time resolution. And geomagnetic storm scale, so generally it is 1 to 5, these are the geomagnetic scale used. So, G1 is the minor, that is Kp 5, then moderate Kp 6, then strong is Kp 7, severe is Kp 8 and extreme is Kp 9. So, in today's thing we have covered basically the interplanetary field IMF is interaction with Earth's magnetosphere, and the result is like geomagnetic storm and substorm. And the last topic we covered, that is the geomagnetic indices like Kp index, K index, CMH, DST, all these things. So, with this conclude today's sessions. Thank you very much.